And for our next talk and for the last talk of the first day, we have Michal Valko and ShantanuThakoor with us. So hello again. Thank you very much for accepting our invitation. So before you start delivering your talk, I would just like to quickly introduce both of you, if that's okay. So Michal is a machine learning scientist in DeepMind Paris and at the SQL team at INRIA. He is also the lecturer of a master course graph in machine learning at Lens Paris Saclay. Michal is primarily interested in designing algorithms that would require as little human supervision as possible, which means reducing the intelligence that humans need to input to the systems, and also minimizing the data that humans need to spend inspecting, classifying, or tuning the algorithms. In addition to that, another important feature of machine learning algorithms should be able to adapt to changing environments. That is why he's working in domains that are able to deal with minimal feedback, such as online learning, bandit algorithms, semi-supervised learning, anomaly detection, and self-supervised learning. He has most recently worked on sequential algorithm with structured decisions, where exploiting the structure leads to provable faster learning. Thank you again, Michal. And ShantanuThakoor is also is a research engineer working at DeepMind. His primary research interests are in graph representation learning and reinforcement learning. Prior to this, he received his master's in a computer science from Stanford University, where he was working on problems in AI safety, neural network verifications, and he is recently interested in applying graph representation learning methods to large-scale problems. And you may have already heard KDD has a challenge, Open Graph Representation of Open Graph Benchmark large-scale challenge, and he's also a part of it. So thank you very much again for being with us today, and the floor is yours.
Thank you very much. Thank you, Onur, for introduction, and thank you, Oznur, and other committee members for the invitation. It's very nice to see you. I've been hoping to visit Turkey for the last 5 years, but I will have to wait a little bit more. I'll just confirm that you can see the slides.
Not yet. Not yet. We can.
Oh, not yet. Okay, so because I see you are sharing the screen.
So, I think you need to stop and then.
Okay, maybe I need to stop and I'll redo it again. Right. How about now?
When this is over, we would want you definitely here in person. Yeah.
Is it working now?
No. Why?
No. Okay. It says
we can see the Chrome window that has the posters of your talk.
Oh, I assumed this is Onur Hoca's window. Is it yours? Then
oh yeah, it's mine. It's mine.
Oh, okay. Then okay. Because we were using it in our slides, I thought it's Onur Hoca's.
I stole it from the internet. Okay. So I thought it was a very beautiful image. So okay, so it works, right? Perfect. Yes. Okay. So I can then it's very good because I can also see you. And I can present. Very good. So today we'll talk about self-supervised learning on graphs, and in particular, how to find representational learning without any labels. And so I'll start to kind of motivate why we are after, in particular in DeepMind, after self-supervised learning. You know, our bigger goal is to create AGI, and for that we would like to agents that.
With apology, yes, I think your screen is in a not full screen mode. One of our attendees pointed that out. So is it possible to turn it into a full screen, or do you prefer it this way?
I think it is. Maybe I can change the. Oh, I see. I see. It's just like a proportion thing. I think now it should be fine.
Okay. Yeah.
Yes. If it needs to be adjusted, I can do that. All right. So if we want to have agents that are intelligent, we cannot train them with a lot of data because that's difficult, right? And one specific aspect of intelligence that these agents should generalize significantly beyond the task that we're trained on, right? But what we have in reality that we can only do really well with huge models and huge amounts of labeled data. Well, this is very difficult because we don't have huge amounts of labeled data, but this is something that we know very well. So we'll try to trick the way, and somehow we'll try to predict things that we already know. And in this talk, we will kind of show you how. And so our hope is that we'll by mastering this self-supervised learning, we equip agents with these stronger generalization capabilities. And, if you think about agents in environments, you can think like, these are the agents that try to, for example, create a map of what they see. So they kind of need to have a representation, something that is very natural for us, but not very natural for agents. So, our bigger goal is to be able to create these kind of representations. All right, so this is what we prepared in the next hour. First I'll talk about the self-supervised learning. I introduced the field, in particular the modern self-supervised learning, because the field exists for a long time. I'll present one method that we introduced in 2020, BAYÖYO. And by particular, we focus first on images, not on the graphs, because it's much simpler to understand it. So we'll try to train the ResNet as a particular encoder, and then ImageNet will be something that we use as our data set. Well, then in the next part, Shantanu will explain the graph method. So in much complicated encoders that is particularly adapted for the graph structure. There are several kinds of these encoders, and Shantanu will briefly describe all of them. And finally, we talked about 2021 work. Some of them was never publicly presented, about how to actually apply this bootstrap way of self-supervision to the graphs. Please interrupt us with any questions, either live, either text. We love all the questions. We don't need to go over all slides. We'll try to adapt as much as possible to explain whatever is useful for you. I also tend to speak very fast, so please slow me down and don't hesitate to just interrupt me anytime. Like, just shout if it's possible, unmute yourself and shout. So unless there are any other questions, then I'll start from the part one. All right. So why do we need this self-supervised learning? In computer vision, the goal is to process an image to solve downstream tasks such as classification, segmentation, the speaker, or object detection. So in the deep learning particular, this is what we do, in this century, right? We first process image with some neural network that we call encoder. And, for next 20 minutes, it will be ResNet. And this representation later is fed to some kind of other downstream networks that, they're specialized for particular tasks. So of the first network, you can think of feature extracting, and the other one is something that's using this extracted feature that are common to all of these tasks. For the network, they're particularly designed for the task. But then how do we train this neural network, and what data we use? So there are kind of two kinds of data that we have in practice. Well, on one side, we have label data, where each image comes with some kind of ground truth information, such as labels for the image, or bounding boxes, right? Like, this is the head and this is the tail. Well, but this is where the human needs to intervene, because that it's this expected cost of labeling. On the other side, we have a lot of unlabeled data. They're relatively cheap, because we just need to capture them, and there was no need of human supervision needed to provide an input. But in this part, we will try to learn how to actually create this encoder. So first, we try to train a generic encoder by using this unlabeled data, so not knowing what is the task. And then we train a downstream networks with, potentially using much less, like, multitude of less labeled data for specific tasks in hand. And so this first part that we're discussing in all this talk, it's called, self-supervised learning, or pre-training, because we're pre-training the network to be used later. And this is, this BAYÖYO approach that we present. It's a way how to, do this pre-training. So how does it work? This is the in the next 50 minutes, I'll present you the paper that we published at NeurIPS in 2020. So one main ingredient of the self-supervised learning is that we take advantage of image transformations. So that means, like, it's not completely free as we put humans the knowledge in the data. Before, we put the labels. Now we're putting the knowledge in some different way. We're telling network that if you do this particular transformation, crops, resize, color destruction, something that you could do automatically. Then you kind of preserve semantic information. So this information is not free, but it's much cheaper to just say, well, you can just do crop and whatever you see on image is exactly the same. It's much easier to say that than here, there are a million pictures and label them. So for example, if we take an image of the dogs, and transform it, it will stay a dog. So more generally, we expect this high-level semantic information to be preserved by the simple transformations. So BAYÖYO and some other self-supervising methods are building on this idea. So specifically, we give a transformed view and image where we look directly to predict one transformed image based from the other. So if this extractor, if this encoder extracted high-level information, and so not some kind of details, it should be easy to predict kind of same high-level information because it's the same. So as both views contain same semantic information, we should be able to predict their representation. That's a big main idea. So how does it work? We first start with some image. We don't know what it is. We don't know that it's a dog. And so, for example, at the same time when we're learning representation for a dog, we're also learning representation for a grass and for a lot of other things, right? We never take image what it is. We do two different transformations, randomly. It's actually very important with which probability, but these are for now details. Then we pass it through a encoder that at the beginning has some random initialized weights. So this is a big image, and an encoder, encodes it to 2048 numbers. This is the output. Then we predict it to something smaller, let's say 256 numbers, of the vector of 256 numbers, and we would like this prediction to be similar to some target labels. But the thing is that we do not know these target labels, right? So it's very important that we kind of only encourage these views to be predictable. So in BAYÖYO, both the prediction and target output network are continuous networks. So to know how to predict things well, we can just simply measure how the things are predicted by some L2 loss. And in particular, we create targets in the following way. So in the beginning of the network, of the training, we do some random initialization. So we predict some labels that are, completely nonsense. They're random initialization, so there is no sense. We try to actually, at the beginning, predict these random labels. So we regress to this random prediction. This is different than predicting random labels, by the way. We're predicting labels that are processed by random network. They're not very good, but it can give you to, like, let's say, few % of accuracy. Well, we're aiming for something much higher than that, but it's not a bad start. But that's very important first step. This sign right here, that means that while we're doing that, we only train this encoder. So we don't back propagate any information, any loss back to this other network. So only the network that's being trained is this encoder. This is fixed, and it is random initialized network. The ResNet with random weight, no training, nothing, right? It's only something that we use to construct the targets. So after we start regressing the predictions on the view to this fixed target representation. So if we do so, a very interesting phenomenon is going to happen. Even if we keep target network fixed to randomly initialized network, this process already allows encoder to learn a better visual representation than is random initialization. So this randomization was going to know something very good, but if we train it to random initialization, we get something better. So our encoder somehow gets stronger. So that is this increased muscles. So from there, a natural idea, this is actually borrowed by reinforcement learning, because that's all we use. It's very similar thing that you in DQN, is to replace this random, and slightly improve encoder. So improves this, random weight with this slightly improved encoder, right? So as a result, now we have slightly better targets because we improved the random weight with slightly better weight. And the regressive. Well, now we have slightly better weight. Now our encoder, as only thing that we keep training, so the training only goes from here to here, so backpropagation only goes from here to here. It gets better. What's next? Well, repeat the process. We take this better encoder, we replace it for our target networks. That's only to create the targets. We create better targets, and then we can train our encoder to get even better. And so it gets even stronger. And just repeat this process until we cannot learn anything else, and so on until convergence. So now that we have this intuition, let's have slightly more detailed look at the architecture that we're using. So first, as I said, we generate these two different views. Actually, it's slightly more complicated. We have several of, let's say, 12 transformation. Each of them we go through a list of the transformation. With each of them apply with certain probability. Maybe 80% we crop, then with 20% we strip the color and so on, and we pass through all this filter until we create this the set of transformation. So this is quite important, and this is part of the tuning of the network. And this was a lot of technical work went to this. Second, each of these images processed by the most standard ResNet, right? For here ResNet 50, to get some kind of image embedding. This is something actually that we at the end output as our final features, right? So these are the features that we get at the end. After that, we project it to the smaller space. Now you could ask, why don't we output this, something that we're predicting? The thing is that, this is smaller dimensional space, so it actually will be easy to, learn this prediction task. But the reason why we don't output as our final features, but because this is small dimensional, and 256 is a kind of too small to, represent all the features necessary for vision tasks. Somehow, 2048 is enough, but projected it's too small. So that's why we don't output as our final output the output of the projection. What we're outputting is just out of the ResNet, because as I said at the beginning, the very outcome of this procedure is just to produce trained ResNet that take any image and output you these 2048 numbers. This is the representation learning, output the embedding in the space of 2048 numbers. So now we project each image, using just multi-layer perceptron to some small dimension, and then we try to learn a prediction. From this projection, we use another multi-layer percenter to predict. And so this is what we do in the online branch, so and only on online branch, where we apply the second predictor to extract this prediction embedding. Now, this predictor is very important because this is kind of something what is different from all the prior work. This makes our kind of CMS architecture, as they're used to calling deep learning, asymmetric. Before, the state-of-the-art methods were using symmetric architecture, and so this is something that makes it asymmetric. So this is something that will not be applied to the second branch. So on the second branch, on the target branch, and we call it target branch because it produces target labels, we add this stop gradient. So when we do the training by backpropagation by just simple stochastic gradient descent or Adam optimizer, this is never being updated. So that's why we put this stop gradient here. So finally, we just compute a cosine similarity, which is just a simple also L2 loss, right? We take the Q theta Z theta minus Z prime C squared, and and if you normalize each of those, so if this is you divide by norm of Q theta, and this is you divide by norm of Q of Z C prime, when you redistribute it, you did exactly this expression, which is the cosine similarity. You can imagine you have two angles, in a 250 6-dimensional space, and you're just kind of measuring the, the angle between each other. This is actually pretty simple. We just want this prediction to be same. We would like the prediction error to be 0. So whenever is this prediction error, we compute it and we propagate it to, again, train only the online network part. So we train these online parameters and online parameters only by gradient descent. And particularly in our work, we use the large optimizer to maximize the similarity. So the main difference between this previous intuition and the BAYÖ is that we don't really copy the weights exactly. We use some exponential moving average. So instead of just copying weights en bloc, we just look at like the previous network, several number of steps, and we exponentially weight, with more recent, with more weight. So this is very useful because it's kind of builds a momentum. It's you stabilize the learning because we average several networks in the past, but it of course gives more weight to the more recent one, exponentially more weight to the recent one. So it's more important. And the reason why we don't do, we could remember the last 100 network and do the average. The reason is computational. Doing exponential moving average, as also known as Polyag averaging, it's very, very easy to do practically, because it means that you take the whole network, you not multiply it by, let's say 0.09, and you add the new numbers. So you actually never need to remember last 100. You can just remember only one, one version of weight, but you're effectively doing average of everything what you had in the past. And this is very important because this network gets very big. And so Shantanu will tell you later, memory matters tremendously. So every single, trick like that, it's life-changing in getting the good performance. All right. So first, the highlights. The key ingredients is that the human knowledge that we put into this is these image transformations. Second important ingredient was that we create these target networks to predict labels, because in unsupervised or self-supervised learning, we have no labels. So we kind of need to create them, because the only thing that we know really to do well in deep learning is to, do the, supervised learning. So we kind of create the labels, and, and this way is, I showed you one specific way to create labels. And the other thing that we did, it was very important, is this additional predictor on the top of the encoder that made this whole structure asymmetric. So additionally, the interest of this procedure, and this is something that Shantanu will use in the second part, this is extremely simple training procedure, because you can just change already existing architectures. But one of the fundamental difference is that, and I'll describe this point next, is that there are no negative examples. And because here we only try to, put, let's say dogs with different kinds of views close together. And the other approach is did something else on top of that. But we don't need to do that. This is also something super important from memory perspective, right? And the other thing that we don't need to work with on embedding, so we can work on embedding level, so we don't need kind of pseudo labels to create. We just directly, do something, and something is just L2 on this embedding. All right. So just a quick turn that, there was a life before this BYOL, and the life, and meaning, best performing methods until now were contrastive. So where they're built on the, very simple idea, and the particular, they were all applied in one very, very crucial benchmark that, that moved the field, of self-supervised learning, and this was ImageNet, right? So there were several of these jumps from a different architecture and different approaches up to the BIOL part was, getting somehow of, over 70 for this SIM-clear approach. And this SIM approach was very similar to what I just presented, with one very crucial difference. They, as I presented, they try to put images of the views of, for example, the dog close together by, by minimizing cosine similarity between the two. But on the top of that, with also similar architecture, they took some other image from the data set, hoping that's not a dog. So of that you are never sure, and we'll try to push them apart. So at the same time, putting things that are similar close together and putting things that are different far from each other. This was something that up till now, until mid 2020, brought the best results. So in bio, we don't have these negative examples, and this has several consequences. And this is why it was such a foundational change in the of paradigm in this field. So first is contextual, that we actually don't need to define what is this not an object. What is the not a dog? It was actually difficult to take a dog and find an image that was not a dog, because you don't know what's on the image. So what was usually done, as you do distributed learning, you try to train things in batches. You pick random thing from a batch. Let's say you have 4,000 images in a batch, and you randomly pick one, and you say, well, let's try to be different than this one. Well, maybe you're right, and maybe you're not right. And so if you're not right, you actually were encoding something that was error. So that was, this default option could be wrong. The second thing, is scalability, to sometimes, and in particular in graphs, to define what is not an object, meaning that we need to, define, a lot of different ways. There's a lot of different ways how image can be not a dog. It could be a cat, it could be different animal. It doesn't need to be an animal. And, for best performance, you kind of had to enumerate all of them. And so this, for best performance, you have to, go, all the way to the quadratic thing. Now with this approach, you don't need to do that. And second thing, that why it was important. So since, you don't need to rely on this negative with respect to something that you don't know it's negative, you can be more robust. Yeah, and I'll present a couple slides on this. So just on performance, how this method performs on images. First, we need to spend a second, like how do actually we measure performance, because we don't have any labels, right? So what kind of things we compute? So one way, how the field decides to measure this performance, that you train this representation without any labels. You get a network that produces numbers, but you don't know how good they are. What you could do, when you freeze this representation, so you said, let's stop training. These are the weights. This is going to be evaluated. So I freeze them and only train one layer, so one linear classifier on top of that. And so if the representation is good, this one layer would able to learn something very good. If this representation is very bad, one layer linear classifier are not going to give you very good results. And so then we report, the results of how much one layer linear classification could do, which is, what we do in supervised learning. We perform the classification. So now the numbers, and this is, first showing how much actually you could do if you, use, all the labels that are available. So this is kind of the upper bound. You cannot do better, do without labels than with the labels. Or, oftentimes you cannot do better because, you could actually learn something better if if the labels could give you something wrong. But this is what the ImageNet gets using ResNet without using labels. Up till our methods approaches without labels, we're getting for example for ResNet 50 up to 69%. With bigger architectures, when you do like twice or four times a bigger architecture, you get to 76. And the method that I just present gets you about that, gets you almost as close to the method that that uses the labels. So by that we kind of close the gap or approach it very well to the approach that had to use the labels. And I to give Shantanu enough time, I'll just spend one things on the robustness, because this is also important. I keep repeating that the most knowledge that we put into these are these augmentations. So the better method would be the least knowledge we need to put, as are the actually are the augmentations. So I'll skip this slide. And one way to test it, you can try to remove it. And if the method decrease performance very well, then it means like it's very sensitive. So our prior methods, which seem clear, if you remove, for example, a grayscale, you get 5 percentage points less. If you, on the top of that, remove the color, you get even 22% less. On the other side, our methods also suffers because you have you're giving the network less knowledge, but it suffers much less. And this is something that's robustness. And I'll skip the other part to give Shantanu enough time to go the second part. So.
Michal, is it okay?
I think I'll let Shantanu to share the slides. And maybe that's also a good time to have any questions if there are some questions.
There are 2 questions on the Q&A, so I can read them out to you. One of them is asking, how can we be sure that BAYÖYO training will converge?
So we cannot be sure by default, but one way is very easy to make sure that it converges. And in thesis, we actually moderate the learning rate. We don't trade a constant rate. We set the learning that we tablet that the slowly decreases. And if the learning rate decreases to 0, then at the end you will have no moving in the weight, and it eventually converges. It's also this is a very good question because a lot of effort went to the learning rate. It's very important which learning you say. Particularly, we have some kind of cosine decrease. At the end, at the beginning, we increase the learning rate up to some point, and then we decrease it, using cosines all the way to 0. But anything that goes all the way to 0 essentially converges. But yes, it's a very good point because since the labels are always changing, the loss function is always changing. So by definition and without taking special care, it may not converge. So it's really good insight that this may not converge, and we take a special care so it does.
And another question is asking why do we prefer measuring cosine similarity instead of L2 difference? They're not exactly the same, right?
They're not exactly the same. They're almost the same up to the normalization. So it's if I could write on the board, like if you actually take the Q divided by norm of Q minus embedding divided norm of embedding squared, you do the product of the two, you actually get the formula. So they are equivalent. The normalized squared difference is equivalent to this cosine similarity. But without this normalization, they're not equivalent.
And we have a question from Zroja, so maybe she can.
So you mentioned at the end that the data augmentation part is the most critical part. And when you start your talk, actually that was the question in my mind too, because thinking this important to the domain that I work in, computational biology, some augmentations could be even dangerous because they are not they are going to be wrong. And the example that you show at the end is also kind of similar. Is it going to be, is the next step going to be like figuring out which of them are useful, which of them are not, and throwing away the bad ones?
That will be really good. So ideally, you would like to actually do even one step further, actually, instead of throwing out, and like maybe learn them, learn which are the kind of augmentations that are very good, or do something, that's like that, which has, at the least possible biases that could encode in the process. And so the actually part that Shantanu will present, he will use actually very simple augmentations. One typical augmentation that has been proven to be useful just almost overall over the graphs, text, or images is just this crop. There's always some version of crop. You can take a sentence and crop it and try to predict the rest. So this is somehow, I don't want to overstate it, but it's close to be universal augmentation or corruption function. All the other ones, whether you do color jittering, histograms, this could be very specific, and sometimes, sometimes can make things better, but sometimes not necessarily.
I was thinking of protein sequences and applying similar ideas, and there this will correspond to kind of adding mutations to the sequence. You are a little bit familiar with the domain, that's why I'm not. So
yes.
that would also mean that you are actually entirely changing the class label.
Possibly you're changing the what you actually believe the molecule should do. Yes, so it is it is possibly not the best possible augmentation that we could do. Indeed.
And a little note, like this idea of like not needing the negative examples is actually, I think, breakthrough. I mean, in your domain, in our domain too, like for example, in many cases, you have positive labels, but you don't have negative labels, like protein-protein interactions. You cannot prove that two proteins do not interact. So in many cases, we make up negative examples. So this is actually very inspiring. I'm gonna think on this and figure out how to make use of this. Yeah,
well, you. I'm happy to also help. So I can also point out some other work that we have done. For example, we try to apply this also with Shantanu to some neural data. It's similar, like neural readings, and try to, because also there is also very difficult to see what is the different neural reading, right? Similar as with molecules. But I think Shantanu will also mention molecules as one of the specific examples. So he may be even in a better place to answer this kind of question.
Great, looking forward to it. Okay, yeah, thank you.
Sounds great. There's one last question before I will just invite Shantanu for his part. So the attendee is asking, how did you decide the probabilities of transformation you used? Were there transformation pairs that performs better than others? Can you give any information from that?
Yes. So there was a lot of fine tuning tried to do. I can tell you. So these actually use even different probabilities for the transformation for the top part, for the online part, and different probabilities for the target part. We tested all the possible combinations, and we picked the best. But I can give you something like the crop is always applied and is the first one. Then, for example, the flip is applied with 50%, and then the color jittering after that with 80%. Then we do the brightness adjustment with 40%, and and so on for 12 different. The least probability has something called hue adjustment and max intensity. And so all of these, up to the second decimal point, we tried, which one worked the best, and these were the ones, the result I'm presenting are with the best presenting, and they are, all described in a paper, that are that describe bio in the appendix B, so if you're able to, just take all these experiments that we did and use the transformation. There has been a lot of prior work also done in transformation before BAYÖYO work by a group of Jeff Hinton that has a SimClear, because they also realized that transformation are also the crucial part, and they did immense the experimental work to actually figure out the set of the right transformations. And most of times in our work we follow what they did.
Thank you very much, Michal. So I think we can continue with Shantanu, and then I will aggregate the questions after his piece. Thank you.
Great. Yeah, thanks a lot. And I'm very happy to be here. And thank you everyone for the invitation and for organizing this wonderful seminar. And I hope you can see my slides. It should be presenting now.
Yes, perfect.
Okay, great. Okay, as I'm gonna assume it's visible. Okay, and yes, please feel free to stop me at any time. I think these questions were all really interesting questions, so let's keep that going. Great, so I think Michal presented a very nice introduction to self-supervised learning on images. And for the rest of this talk, we'll focus more on graphs. This is work done with all of these amazing people listed here. Okay. So let's start from the absolute beginning, because maybe people don't have much background in graph learning. So graphs are nothing but data with some kind of special structure. So the basic building blocks of them are nodes, which are the entities over which we work. Edges are connections between these nodes. And graph is just a collection of nodes and the connections between them. And each of these, of nodes, edges, and graphs, can have different features associated with them. So at the bottom, we just see these cartoonish examples of graphs. But actually, in real life applications, we see graphs everywhere. So for example, in transportation networks, like we use in Google Maps, these can very naturally be modeled as graphs. We can think of the intersection points in our maps as nodes, and the roads connecting different nodes can be our edges in our graph. And here there are also many natural features that just pop out once you model the data set like this. For example, you can have the length of the road or the amount of time it usually takes to travel across it as features for the edge. And one possible task we would be interested in doing here would be ETA prediction. So trying to predict how long does it take to get from one node in the graph to some other node. To give another example from chemistry, actually even molecules can be represented as graphs, as we were just discussing. So you can think of atoms being the nodes and the bonds between atoms being the edges. And again, you have very natural features like the atomic type, the charge, maybe atomic weight, the type of the bond between the atoms. And maybe a task could be to predict whether this given molecule inhibits certain diseases, or it could be used as a drug in a cure for some disease. So this was basically an introduction to what graph structured data looks like. And we're interested in doing machine learning on graphs. So how does the learning actually proceed? So usually start with this graph. And like other forms of deep learning, we use neural networks, specifically a special type of neural network called a graph neural network to produce these latents. And depending on the kind of task we're interested in, we can have latents at the node level. So we would learn a representation for each node in the graph, maybe to do node classification. We could learn something at the graph level to predict properties of the entire graph or maybe a subgraph. And we could learn embeddings at the edge level, maybe to predict formation of new links or connections between the different nodes in the future. So what do these graph neural networks actually look like? We can think of it as, first we can ask ourselves, what are our desired properties in such a neural network which acts over graphs? First, of course, we will want to use the graph structure. So we want to use the node features and the edge features, and also take advantage of the connections between the different nodes. And we should also not be sensitive to the order in which these nodes or the neighbors of each node are presented to the network. So we want some notions of permutation equivariance or invariance. So for example, in this molecule, it shouldn't matter if I tell you first some hydrogen and then an oxygen and then nitrogen or something. The output of the network should be the same, no matter what order we see these nodes in. And this is very different from, let's say, language processing, where of course the order of the words matters a lot. And you can use something like a recurrent neural network for this. So as a starting point, let's again take some inspiration from the images domain. So we all are familiar with convolutional neural networks. So the basic unit of computation in this is this kernel, which is a fixed kernel which slices across the image to produce representations of different patches along the image, as we can see here. And we know one nice property of this is that these encode certain inductive biases like translational invariance, which means that the output is mostly unchanged by the image, the objects in the image, like shifting slight amounts. And patterns are interesting, no matter where they occur in the image. So the same kernel is slid across the entire input image. There are also notions of locality. So for a certain patch, the neighboring pixels will affect the representations at that point, much more than the values of very far off pixels in the image. And if we take a step back, we can notice that images are essentially a special case of graphs where the different pixels in the image can be thought of as nodes, and they're arranged in this grid connectivity pattern. So we see that for this special case of graphs, convolutional neural networks work very well. And now we can think of what happens in arbitrarily structured graphs. So for general graphs, there are concepts of graph convolutional networks, or GCNs. The way these work is each node aggregates information from all of its neighbors with some fixed multiplicative weights Cij. So for example, in this example, node B will be collecting information from nodes A, C, D, and E. And of course, at the end, we want to be invariant to the order in which we process information from these four nodes. So it's like A first, C first, D first, or E first. So it would collect all of these features of the neighbors And then at the end, take some reduction of them, like max, sum, or average, which is invariant to the order in which you process them. And at the end, the representation of node B at the next layer in our neural network will just be a function of its neighbors and perhaps itself. And there are many different ways of computing these weights C, ij between the different pairs of neighbors. And these depend on the adjacency matrix of the graph, which is basically the edge structure of the graph. And it's worth noting that these are especially useful for homophilous graphs, that is, graphs where two nodes being close together in the graph means that they have the same kind of behavior. So especially when edges denote label similarity, these are very powerful models to use. And very quickly going over some other types of networks. So on the left, we have convolutional networks. In the middle, we have attentional networks, which are very similar, except they're more powerful because they allow the computation of an attention mask. And this allows a node, let's say node B, to, for example, pay much more attention to its neighbor A than to neighbor C, D, or E. And this could be useful for non-homophilous graphs, where maybe you don't want to pay attention to all of your neighbors because the graph structure is very different. And on the right, we have message passing neural networks, which are much more expressive and much more general than these two, but they're also a bit harder to train and harder to scale up just because they're much more complex. Okay, so now that we know what graphs are and what graph neural networks look like, what is our goal? So again, our goal is to learn meaningful representations. And here we focus on node representations without any kind of supervision. And the reason we want to do so is, especially for graphs, unlabeled data is very, very cheap compared to labels for graphs. And you can use this to pre-train, say, some GCN for a very wide range of many downstream tasks. And even when you have labels, it can be useful to have this auxiliary signal for semi-supervised learning. So for example, starting with this graph on the left, where let's say these colors denote different classes, we want to use a GCN to project them down to these two-dimensional representations, such that the structure of the coordinates is resulting in these clusters, which actually respect the classes of the original nodes. Okay, so let's look at some early methods for graph representation learning. So what makes an embedding good intuitively? So we know that graphs are very interesting because they carry these powerful structure, and good node representations should somehow capture this structure. This is what we want. The simplest notion of structure is each edge, right? The connection between the nodes. So let's say we had some nice graph representation where the representations learned for a pair of nodes I and J. Just looking at these two representations, you could predict whether an edge was existing between them or not. In other words, this representation captures this edge structure. Then we would be quite happy with that. These early methods, which worked on random walk objectives, are a slight generalization of this, where instead of looking at an edge occurring between two nodes, they look at whether these two nodes are close together in the graph somehow. That is, they co-occur in a short random walk. And these methods are very similar to those used in NLP, such as word-to-vec. Yeah. These methods were very powerful, and they actually dominated unsupervised representation learning before GNNs became popular, such as deep walk and node-to-vec were some powerful methods. The problem is they don't scale to large graphs very easily, and they also don't work well with GNN encoders. So they used to actually learn a different vector representation per node, the way in word-to-vec you have a different vector representation per word. So fast forward a couple of years, and currently all the hot methods in graph representation learning are contrastive. So basically, they learn by pushing together similar objects and pulling apart dissimilar objects. And the second step of pulling apart dissimilar objects is very important, because otherwise everything could just collapse into the same representation. But our aim is specifically in graphs is to stop contrasting these dissimilar objects. So we want to get rid of this second step. But why is that? So we can look at the drawbacks of contrastive methods through a couple of case studies. One of the very first methods was called Deep Graph Infomax. How this works is you start with your input graph. You also have a corrupted or a negative graph, which is realistic but semantically dissimilar from the input graph. You have node embeddings for the input and for the negative graph, and this input global summary of this input graph. You pull together all these nodes towards this central global summary, and you push apart all the negative node embeddings from this one. And this works great. In practice, it gets good performance. The problem is it's very hard to define this corrupted graph, especially in the graphs domain. And the reason is, for graphs, many data sets consist of only a single graph. So for something like ImageNet, you could take a single image here, and you could randomly choose a different image from your data set to use as the fake, the negative example. And probably this is going to be a very realistic image and going to be semantically very different from the original one. But here, since you only start with a single graph, you can't actually find an other graph. So it's a question of computing negatives rather than finding a negative. And this is a much harder problem. After that, there was a method called Grace, which is still contrastive, but it's on the node level rather than the graph level. That is, it starts with a single graph, then it forms two augmentations or two different views of this graph. And both of these are semantically similar to the original graph. So we never want to construct a dissimilar object. And we say positive examples are each node across the two different views. So the same node in the two different augmentations. And each negative, the negative example is every other pair of nodes. So this is great because it gets rid of the problem of having to construct a negative graph. But the problem is that this the contrastive objective is quadratic now, because you're comparing every node to every other node. So if you have a graph with n nodes, this takes n square memory. And for large graphs, this very quickly runs out of memory. And there are some ideas you could subsample negatives instead of using all of them, but this makes performance suffer. And this is a hard problem for large graphs. Okay, so to solve these issues, we were applying the BYOL methodology to graphs and calling it Bootstrapped Graph Latents, or BGRL. Yes, so the key idea is to bootstrap embeddings from each node so that we don't need negative examples. So very quickly, I'll go through the framework. So given a graph, we want to generate two augmented views. This is very similar to the approach Michal presented for images. And the augmentations, again, are transformations with respect to which we want our embeddings to be invariant. We have these two GNN encoders, theta and phi, to form these two latents, H1 and H2. Again, we have a predictor P theta to form a target prediction Z1. And we want Z1 to be similar to H2. That is, H1 is predictive of H2. And we do this by flowing gradients through theta to maximize the cosine similarity of Z1 and H2. And we block the gradients through phi. And again, phi is updated as a exponentially moving average of the online parameters theta. And a slight adaptation from BAYÖYO is that we don't use the projector network here, because in practice, graph datasets are much smaller than image datasets. So the problem of, we require 2048 dimensions for the main task, but that's hard to predict and so on, which was there for images, just does not apply here anymore. And actually, it slightly slows down learning due to there being a more indirect learning signal. Okay, and just finally, one note on graph augmentations. So this is a design decision. And basically, we want these to be perturbations that don't change the semantics of the underlying object. For images, these are very intuitive because, let's say you're trying to do image classification, mostly flipping or cropping or distorting the color wouldn't actually change the class. So through human knowledge, we can actually add this to our framework. But for graphs, it's actually very unintuitive because we don't know how, what kind of changes would actually change the semantics of the graph. And another problem is that we want to apply the augmentations to the entire graph, but we're learning embeddings at the node level. So that's kind of like augmenting an entire image, but learning pixel level representations. So it's a much different problem. So in practice, we only do some simple, cheap augmentations, like randomly dropping some edges or randomly masking some features. And this is not at all perfect, and it's still a very open area of research. I'll quickly go through some experiments. I think I'm basically out of time. So yes, we use the same linear evaluation protocol that Michal mentioned. Yeah, one important thing is that even randomly initialized GCNs are actually very powerful because their inductive biases are very powerful, and they can even surpass pure supervised learning. So I'll just present everything relative to a randomly initialized GCN. I'll skip the data sets. Okay, these are just some small data sets of around 10,000 nodes where the quadratic computation that Grace tries to do is possible. And we see that Grace and BGRL, which are the red and the yellow, are very competitive, both with each other and with fully supervised learning. But what's nice is that BGRL actually uses 5 to 10 times less memory. So that's quite nice. Scaling up to a larger graph, which has 170,000 nodes, where the Grace quadratic approach cannot work at all. We see that, basically we see that you need more and more negative examples sampled for Grace to actually perform better and better. And you need around 2048 negative examples to be competitive with BGRL. Yes, finally, I might skip this, but basically graph attentional encoders previously were not able to be trained by methods like Grace, but BGRL is able to train them in a very stable manner. So here we see the attention distribution that the attentional encoder learns, and it's much more stable for BGRL and for different instantiations of Grace. And it also gets to a much higher performance. And very recent news is that we were working on this KDD Cup 2021, which was this open graph benchmark large scale challenge, which had a node classification data set with around 240 million nodes and 1 billion edges. And BGRL was one of the key parts of our approach to be in the top 3. And this was a very interesting result because we see that BGRL now works even in the very, very high data regime. It works also with the very expressive message passing neural networks that I described earlier. And here, instead of taking the frozen or linear evaluation protocol, where you first train the encoder and then train the linear classifier, we just mixed both of the losses at once because the problem is much more complex and difficult to learn only with that linear evaluation protocol. And it still works very well in practice. So it's quite valuable to know that directly mixing BGRL with supervised signals still works well. So the main takeaways is that it's competitive with contrastive methods without using negative examples. There can be some huge wins in memory and performance. And it's also more easily applied to larger graphs because it requires less design choices. And in the future, one could think of extending this to graph level embeddings, or looking at even stronger encoders, or looking at stronger graph-based augmentations. Because as Michal said, this is really the important knowledge that we are imparting. So yeah, this needs to be improved. And yes, that's it. Let's have some questions. Thank you.
Thank you very much, Shantu. So I'm just gonna gather the questions from Q&A, but I see Berin Hoca has a question, so maybe I can first take her question.
Yes, so very interesting work and nice talks, so thank you. My question is about the first part. When I saw that you're doing setting the target with a random initialization, I thought this may be unstable or maybe require a large batch size. Maybe you want to say something about that. And also the predictor module is also very important. Maybe you can repeat the motivation about that once more.
Okay. Was that for the first half of the talk or the second?
First half of the talk.
Yeah, I'm happy to talk about it. If Michal is around, he might want to chime in.
Yeah.
I don't know if he is.
Here, yeah, but you can give an answer.
Okay, sure. Yes. So, sorry, can you repeat the question? Like, it was
So,
about the batch size?
yeah, so A is with the random initialization of the target, is it hard to train this network or require a large batch, mini batch size and so on? And the second,
Right. So,
you want to repeat something about the predictor network, but that I can
right.
wait.
Right. Yeah, so the target network, if it were only randomly initialized, and so the exponentially moving average part is actually really critical, right? And if it were randomly initialized and fixed and it were never updated, then absolutely like learning does not progress at all. And we see that actually we do different ablations about the speed of this exponentially moving average, like how fast it tracks the progress of the online network. And it's actually quite sensitive to that. So if it tracks it exactly and you do a straight copy at each iteration, learning doesn't work. And on the extreme other end, if it tracks it way too slowly and it was essentially fixed, also learning does not work. But somewhere around like 0.9 to 0.99, 0.999, those numbers work pretty consistently. Yeah, so I hope that answers your first question. And for the second one, it was about the predictor. So at least in the graph one, we just used an MLP predictor. We didn't try to use any GNN predictors or anything. Mostly what we want is if the predictor is near optimal, then you can show that this means that the, I think the variance of the embeddings is always going to increase. So this means that the embeddings will not collapse. Yeah, I think Michal probably can say a bit more about this.
Yes, and if you can actually show the hidden slide number 39, if you have time. So we actually tried these ways without the predictor. And if you remove the predictor, that means that that it does not work. So, there is, the reason why we do it, we actually need to, contradict this effect of collapsing, right? Because in general, I suppose like that, the constant embedding, which is absolutely uninformative, is also a good solution for this loss function. So it's important to have several things in place. And in this table, thank you, Shantanu, that is showing like what kind of things put in place, right? So if we don't want to use negative examples, which is in the column beta equals to 0, the only combination that doesn't get close to 0% is the one where you use both predictor and target network. If we remove predictor, last three columns, that doesn't work. We need to have both predictor and target network. There is, however, a way how we can replace this predictor, as Shantanu was saying, making it close to perfect. And instead of using actually a specific, we could remove the target network and replace with predictor that has a higher learning rate than the rest of the network. Let's say 10 times higher learning rate. This is actually the next slide. And that times we can get closer to the optimal performance. But it's only closer, right? The optimal performance is 72. We can get with 10 times to 66. So it's more like for understanding that there are things that we could do similarly, but it seems quite important that we need to have these things in place, because without that it doesn't work.
Thank you very much, Michal. So I have one question. So I think this idea behind BAYÖYO is quite fascinating. And it reminds me, like here you start and get sophisticated levels as each iteration, which reminds me the framework of curriculum learning, where you introduce with a simple instances, and then as time progresses at different epochs that you have more complicated examples to train on. So can there be a combination of these two both? So because at each time that you rearrange the random network, you also see where your target variables and your predictions are close or mismatched. So you may also guess like the easier and harder instances to incorporate both of these ideas together.
I think one of them is actually already kind of using this curriculum, as you notice, like we actually using actually very simple way of curriculum learning, just using the average of past predictions, right? So our curriculum is very simple, something that stabilizes. We actually were motivating with something, by a prior work called PBL, Predictive Bootstrap Latents, that's coming from RL, which is motivating itself by DQM. And the thing is very simple, in deep learning, we know how to predict by supervised learning with labels, things that are stable. If we actually were directly predicting things are changing, we will be doing very bad. We tried, it didn't work. The way of making it stable to something, it's kind of unlock the power of what we can do with deep learning. So it's kind of a trick to use this thing. Then you're right. You can do much smarter way how to predict to, right? The thing is, like in curriculum learning, sometimes it's like that. There's also another human input needed to design a good curriculum learning. Here, we try to design kind of out of nothing, right? That's why it's called bootstrapping. We start from really nothing, with prediction of network with learner labels, and try to bootstrap on that. And when we said, well, this is better than something, we use that, right? So there is a simple way of curriculum. It doesn't preclude that could be much smarter way of curriculum. I believe there exists. The question that we don't know how to answer is how to get there. The thing that exists is almost sure. The how to get there without any information. I think that's quite open, and I don't have any idea how we would design such a thing.
Thank you very much. So I can see 3 questions in the Q&A. If there's no other question from the panel, maybe I can start pointing them out to you. So one of the questions is asking, are you embedding every node at every prediction step? And in parentheses, they are saying comparing branches.
Hello?
Hi, Shantanu. Yeah, we can hear you.
Yeah. I think my internet just, yeah, there was a problem.
So do you want me to repeat the question? So the question was asking, are you embedding every node at every prediction step?
Yes. So basically, for each update step, we do full graph learning for most of the data sets, except for the OGB challenge where we couldn't fit the entire graph in memory. So we do full graph learning. That is, we embed every single node at once. We do the predictions for all of them. And we we maximize the mean cosine distance over all of the nodes in the graph at once. And this is actually, I think, the most popular way of doing things. When graphs are small enough that you can do this. And for larger graphs, what you have to do is you have to subsample the neighborhood around each graph, and then you can no longer do this.
And in another question, they're asking, what are your memory costs for the graph self-supervised network? Also, which parts did you learn exactly?
Yes, so am I still sharing screen? Yeah, basically the main part of the memory consumption is not in the computation of the embeddings, but rather in the computation of the contrastive loss. So most of these graph methods like GCNs and GATs and NPNNs, they're all linear in the size of the graph, both nodes and edges. And the problem actually becomes when we try to, so that part consumes actually very little memory, around like 500 MB at most in all of the data sets that we're working on, or maybe like a couple of GB. And the problem is when you actually do the contrastive loss for grace, when you're doing this, yeah, it's just quadratic. So I can actually look for a table, but basically our memory for BGRL increases linearly, and we take between 2 GB to I think 11 GB for all of our data sets. And for grace, very quickly we exceed that, and yeah, learning is not feasible.
Thank you very much. And we have one last question, and this is not a technical one, but considering our audience is mostly graduate students and some researchers from the industry, they are quite interested in this type of question as well. So they are basically asking any recommendation for a fresh graduate student. I guess you are impressed with your CV, having your master's degree from Stanford and starting to work on DeepMind. So do you have any suggestions? And I can also ask the same question for Michal, for their team and how they are considering fresh graduate students.
Yeah, I think, I guess I was also like a fresh graduate student 2 years ago. So I think the best advice that I had gotten at that time was just find something you're very interested in and work in that like a lot. And I found that just finding one thing, like at the time I was working on something completely different, like safety and verification, which I was very interested in. And I found it more useful to go deep into that one subject rather than learn a bit about many different things, and rather just do some interesting research and what was exciting me at the time. And yeah, I feel that if you get very deep in one thing, then you learn some transferable skills, and then going into a different field can also be a bit easier at that point.
Thank you very much. So, Michal, do you have anything to add or about your team?
I agree completely with Shantanu. I think it's good to dedicate sometimes, like there's no easy shortcuts to do. But one thing that I will add, that it's actually not very good to like copy, for example, the CV of somebody, because even in DeepMind, we don't need to have a copy of Michal and maybe, or anybody else, and so it's actually good to, that you find something that you're interested in, have some kind of build unique skill, that you can come to, any other institute or place and, increase and better the place. So I think that's something that I would suggest, focus rather not on copying or being dedicated, being an expert in something.
Thank you very much. So is there any last comments, question from the panelists? So that was a great day. That was quite awesome. So thank you, Michal. Thank you, Shantanu, for being with us today.
Thank you so much. I mean, I don't have any further questions.
Thank you very much.
Thanks once more. The last couple of weeks were like end of semester here. We were all like doing grading and like service work, and now listening these research talks were very refreshing. Thank you so much for accepting our invitation once more. Yeah.
Thank you. Thank you.
Thank you. This was a great experience. Thanks for everyone.
Thanks, Shantanu.
Bye-bye. Let's end this.
Bye, everyone. Thank you.
Thank you very much. Have a fantastic day. Bye. And for our participants, tomorrow is going to be our second day. And the theme for the day will be the performance. Okay, I can switch to Turkish. So the ikinci günün teması performansın ötesi olacak. Yarın sabah başlıyoruz programımıza. Sabah 10'da başlayacağız. İki konuşmamız olacak. Yücel Saygın ve Cem Say Hoca'dan. Sonrasında kısa bir molamız. 2 konuşmayla devam edeceğiz. Bir öğle aramız olacak. Sonrasında bir konuşmamız ve bir keynote speaker'ımız olacak etkinlikte. Özgür Hocam, Berin Hocam, eklemek istediğiniz, duyuru olarak yapmak istediğiniz şeyler var mı? Ben sözü size bırakayım.
Benim yok. Zaten çok vaktimizi de aştık. Daha fazla vakit almadan yarın görüşmek üzere diyorum ben. Berin Hocam yoksa.
Evet, akşama dinlenin, yarına hazır olalım. Yepyeni güzel konuşmaları. Yarına görüşmek üzere.
Yarına görüşmek üzere, evet.